Hello everyone, I'm here to tell you about deep learning in chest x-rays, give you a nice introduction to working with this type of data and hopefully give you some tips and tricks to understand the context in which you're working. So I won't bury the lead. There's only three things I hope that you take away from this tutorial. The first one is that it's really important to learn about the domain you are working in to understand the context in which the data are collected and which they are used. Along the same lines, it's very important to understand the data generating process. What I mean by this is, why are these images collected? Why is this information collected? In what context is it collected? And understanding what impacts that context could have on your models that you build. And finally, I think it's very, very important to understand what data you don't have. So what information could be used by a domain expert to make a prognostication, for example, which you are not incorporating in your model, and what could be the consequences of that. So chest radiographs, a very interesting modality. Basically, you're taking an image of the chest or the thorax, right? And you're getting a nice image of the heart, and you're getting a nice image of the lungs. And of course, you can see some other anatomy in there. And the main idea is to look for anything that's sort of abnormal that you might not expect and try to incorporate that into the current clinical context of the patient and see if you can figure out maybe a pathology. So what do we really look for in these chest x-rays? Well, we're looking for, as I said, an abnormality in the heart or a pathology in the heart. So here's an example of an x-ray where the heart is very, very large. And this tends to indicate that the heart is working very hard, which means that there may be some sort of illness along those lines, something like congestive heart failure, right? Alternatively, of course, you're also looking at the lungs. You're looking for what you want to see in a good pair of lungs, right? Nice, full of air. So if you see some kind of water in there pooling at the bottom, especially, then that's clearly something that you want to understand why that's happening, and maybe figure out if you can help the individual to overcome this illness. But it's not necessarily just water, right? It could be any type of fluid, and you know, we're talking about the body, so it's not water that we're talking about. We're talking about sort of a general fluid, but in some contexts you can actually interpret that it may not be the sort of generic plasma. It may be blood sort of leaking into the lungs, or some sort of pus, and then you're interpreting it differently. So you're sort of using a lot of physical laws and physical principles to interpret this image and try and understand what's going on with the patient from the image. So it's very interesting. Basically, radiologists have this very strong mental model of what should be in a sort of chest x-ray and in a medical image in general, and they're able to use this sort of prior knowledge to understand pathology. And so I won't say that all these parts of the anatomy are actually visible on every chest X-ray, but you know they're there, so you're able to understand that if something is unusual about a certain area, it may be because something is unusual about that part of the anatomy. So why should we do machine learning in this context? It's always important to ask sort of why should we bring machine learning AI into this field? What are the sort of ethical implications of doing that? And when it comes to radiology, there's actually quite a limit on the number of human resources. So if you look at resource constrained countries or regions, there are very few radiologists for the general population. And it's just widely known that any delays in medical imaging are all across the board bad, right? You want to understand what's going on with the patient as early as possible to help them as early as possible. And it's not just limited to resource constrained areas. Even in very resource rich areas like the United States, rural areas tend to not have that many radiologists, and it's an important consideration for those areas as well. So, okay, so what do we need to do machine learning? You know, pretty straightforward, right? We need some data, we need some models, and of course we need a lot of free time to tinker with those data and tinker with those models. So let's go ahead on this journey, and let's try and build some machine learning classifiers for chest x-rays. So happily, a few years ago, the NIH came to the rescue. There actually used to be only 4,000, 5,000 chest X-ray images publicly available for machine learning. And then the NIH came along and they released a data set of over 100,000 images. Lots of excitement here because now you're talking about a large enough size that you can use some of these very fancy automated feature extractors that we call deep neural networks. And a very exciting time because these images also came with 14 labels, which meant you could do supervised learning, which we were getting and we continue to get very, very good at when it comes to imaging. Great. Okay. Definitely NIH were not the only ones who started to share data. My group personally, we shared a data set, and there are others as well. I tried to come up with a list of all the different data sets, but I can't really keep up, which is great because there's a lot of data sharing in this area, and radiology really seems to be an area which is embracing this sort of AI craze. So, there's actually a lot of data out there, slightly different formats, very important to consider the different resolutions and image data types. For example, some of these data sets actually come as DICOMs, right? And a DICOM is a very, very high resolution image, which also comes with metadata. It's a very standard format in medical imaging, but there are some interesting aspects of that high resolution. For example, DICOMs are actually 16-bit, which is higher bit depth than you can see with your human eye. So when they're visualizing a DICOM, they actually truncate the resolution. It's in a process called windowing, so you can actually visualize what's going on with your eyes. So there's actually higher resolution in native DICOMs than there are in PNGs and JPEGs and those sort of compressed or uncompressed image formats for that reason. So very important to actually consider the data type that you're using. But there's a lot to sort of work with, which is very exciting. So, okay. And actually, one particular thing I found interesting is within 1 or 2 days, 3 groups independently published chest X-ray data sets. So we went from basically the NIH chest X-ray data set being the sort of dominant source of data to all of a sudden there are 4 different databases with over 800,000 chest X-rays. So it was really great, and there's a lot of research that has been done because these data were made available. So great, we have some data. Now we need some models. I won't get into the details of computer vision. There's a lot in this conference which does a better job at explaining recent advances than I could ever do. But we're going to really use a dense net here. This was just something, when people were trying out a few different models, dense nets seem to work fairly well. So most chest X-ray models are sort of based on a dense net architecture. But I don't think it's particularly important to consider only this architecture, and I'm sure the lessons hold for other architectures as well. Okay, so we have data and we have models, and this is basically what led to a paper called CheXNet a few years ago, where they took the NIH data set of chest X-rays, they classified them into pneumonia or not pneumonia, and they used a dense net. And this was a very sort of exciting paper because it actually purported to do as well as radiologists in classifying these chest X-rays. Now, there are a lot of caveats when you say you're as good as a domain expert, and I highly recommend reading the blog post that I linked to at the bottom there, which sort of talks about how you should actually evaluate humans when comparing to your algorithm. And the sort of the short version of it is that the radiologists were evaluated in an environment that wasn't true to their daily practice. So they are using smaller sort of compressed images, with only 1,000 by 1,000 resolution, right? This is what the data set came out with, which is very different than their normal environment, where they are able to zoom and window, like I mentioned earlier, and also see previous images for the patient and read about their clinical context. So it's a very different environment. I think it's fair to say that that's not a true test of a radiologist's performance, but clearly the model did well, right? If it was even asking those questions. So very sort of interesting work there. However, when you looked at some of the saliency maps, so if we look at where is the algorithm driving a lot of the predictions for pneumonia? In some cases, it was very good. So if you look at the image with the thumbs up, right? This was identifying opacities in the lung, which are associated with pneumonia. And there were sort of multifocal opacities, in multiple places. So it was great. It was identifying regions that a radiologist would identify to come up with the diagnosis of pneumonia, right? But if you looked at some of the other images, it was looking a little bit all over the place, which was weird. And in particular, it was looking at regions outside of the lungs, which does not make sense for pneumonia, because pneumonia is a condition that you find in the lungs. So you shouldn't really be using information outside of the lungs in order to make that diagnosis. And if you are, something weird is going on. And again, it's very important to understand the data generating process. So if you actually look at x-rays and medical imaging in general, it's very interesting. It's very, very protocolized, right? So when you're thinking about natural images, right, and all the data sets we have of natural images, it's people taking pictures in all sorts of different environments. Objects are rotated, objects are far away, close to you, and there's also sorts of considerations in managing that. But with an X-ray and with medical imaging in general, there is a technician who is trying as much as possible to measure the patient in the exact same way every time, right? So there's two different mechanisms of taking a frontal X-ray. There's AP and PA, anterior, posterior, and posterior, anterior, right? So front to back and back to front. And these two imaging approaches, these two ways of having the patient stand during imaging, have big impacts on the way the image looks. So if you look at the front to back, anterior, posterior view, right, you can actually see that the heart is bigger, right? And if you think about the physics of the situation, that's because you are shining, X-rays, or let's just pretend it's a light. You're shining a light, and the heart is casting a bigger shadow on the actual imaging plane, right? So this means that a heart could look bigger if you take it in AP than PA, which means that if you're diagnosing, say, cardiomegaly or a big heart, you actually need to factor in the orientation of the patient, right? So that's one big factor, right, that we need to consider. Not all these X-rays aren't all measured in the same way, and this could have an impact on our model's performance. And you can see a lot of different subtle aspects of the image which drive these differences. But also, by the nature of the measurement, many sort of systems actually write down the orientation of the patient and whether it was a portable X-ray which took it or a non-portable X-ray. And AP images tend to be portable because you're usually always going for a PA, but if the patient is really sick, then you'll do an AP. And so you can see this image at the top right. It says AP erect portable. It's telling you, oh, this is how I took this image, so make sure you factor in this context. And of course, a model can pick up on this. It can read these words and it can say, oh, if this is AP erect, then this patient couldn't come to the radiology department. That means this patient is sick. That means maybe they have pneumonia. And the models actually do pick up on this type of information. There's a very good paper which sort of explicitly models this, where they try to classify the hospital from which an X-ray came. Not any finding, not any diagnosis. They just tried to say which hospital did this X-ray come from. And they're able to get almost perfect performance because the tag that is used to indicate which side of the patient is the left side was different between the two hospitals. And there are all sorts of these process features which can leak into your model and drive up performance when classifying a radiologic finding, but not actually be using causal features. And so we see this in a very recent paper where they're actually explicitly evaluating the saliency maps against radiologist segmentations. And in some instances, it's very good in that the saliency maps are very consistent with what a radiologist would annotate. But in some instances, it's fairly poor, and it's reasonable to assume that the model is using some sort of process factor in order to classify the radiologic finding, which is not what we want, right? We want it to use the causal features so that we know that the model will generalize, or at least we know that it's more likely to generalize. That's our sort of running hypothesis. Okay, so what do we do about this? Well, we can block out the non-causal factors, and we saw a lot of this sort of research when trying to analyze sort of conditions of the lungs, where let's just isolate only the lung, and then let's build our model with only the lung, and then we know for sure that our model has to use the sort of lung features. Segmentation is a hard problem, so this is harder than it sounds, but it makes sense and it's reasonable. What's our other solution? Well, we could actually explicitly model these non-causal factors. So we can sort of almost add a regularization term, which says, okay, I know that these two X-rays were measured at different hospitals, and that's what domain is in this figure. So I am just going to explicitly try to model that those two different hospitals, and then I want to subtract that sort of learning from my underlying representation. Two different ways of tackling the sort of similar issue of these non-causal factors. Finally, there's a very interesting, more sort of stats-oriented approach, which is just stratify your patient population appropriately. So if you look at this sort of middle figure, you can actually see that the source of the X-ray and the view projection actually clusters these X-rays very nicely. So which machine you use has a big impact on the representation that is learned from the sort of neural network. And so if you actually stratify your population and remove this information from the sort of data, then in some instances the model actually is unable to learn anymore. So in this instance, they were looking at hip fractures. When they remove the information about the scanner model, when they remove the information about what orientation you were taking the X-ray, they actually found that the model had chance performance at classifying fractures, which is a little bit scary, right? So you can't just do a cross-sectional study of these X-rays. You really have to think about this data generating process. Okay, second issue is that we're very often using noisy labels. So here's an example of an actual radiology report, and I've bolded a section there where it says underlying interstitial lung disease slightly limits evaluation for pneumonia, but no new large opacities are detected. Now, if you put on your radiologist brain, okay, this is basically saying, you know, it's a little bit hard to see, but I don't see any big white spots in the lung, so I don't think they have pneumonia, right? However, our NLP algorithm has actually said that this is positive for pneumonia because it hasn't quite been able to interpret the sentence to negate the mention of pneumonia, right? And this is what I mean when I say this is a challenging problem. You know, understanding natural language is sort of AI hard, NP hard, whatever you want to call it. And so, right, this is not going to be easy to solve. But of course, there are solutions, right? So here is a before I get to the solutions, here's sort of highlighting this issue. This issue happened with the NIH data set. They were pretty explicit about their NLP performance in the sort of publishing paper, but a manual inspection of the data found that there were these sort of inconsistencies between the image and the label. And in fact, research is still trying to figure out ways of managing the fact that your NLP algorithm won't always be 100% accurate, and you just have to deal with that noisy label because it's impractical to have a domain expert label thousands of chest X-rays. Okay, so solution number one, right? Just improve the natural language processing. Just solve natural language processing. It's not that difficult, right? We can just, you know, at this CVPR, we can yell at all the NLP people to do a better job, right? So, you know, you'll actually hear about some improvements to the NLP algorithms in later sessions from Ivan. And so, you know, I won't talk too much about this, but this is definitely something that you can improve upon. The second one is sort of to learn with noisy labels, right? Just explicitly acknowledge that your labels will be noisy, and let's model that noise, and let's not treat the label as perfect, but let's treat it as sort of a probabilistic label, which may or may not be correct. And so there's some interesting work in sort of adopting these learning with noisy label approaches to radiology reports and learning with chest X-rays. Okay, so our third and sort of final issue is that we're not incorporating the clinical context. So when I showed this to a colleague, they asked me, why is the chest X-ray and the radiology report in a Hoover? So this analogy clearly doesn't work for everybody, but basically we can't look at these two data modalities in a vacuum. That was what it was meant to be, a vacuum. Let's look at an example, right? Okay, let's pretend we're radiologists again, and we have a chest x-ray, and it's for a 78-year-old woman, and so we're going to write the findings section. So we are going to write what we see in this chest x-ray that's sort of relevant to the patient's health, and which just sort of describes it. Okay, you can try and write it yourself. I've written one myself. Okay, so I can see that the patient has 12 ribs, okay, and they have 2 clavicles. They have both their lungs, which is great, and their heart is between their lungs, right? I don't see any fractures in the clavicles. I can kind of see one arm, but not the other. Okay, so you get my point, right? Is that there's a lot in the chest x-ray which we could describe, which we don't, right? Because it's not relevant to the patient's care. And when you're looking at a chest x-ray or a medical image, it's very important to acknowledge that the radiology report is not someone annotating an image for fun, right? It is someone who is looking at an image and answering a clinical question. So there is an indication section where the person who ordered the image says, look, this is the individual, right? And they have this going on and they have this going on. And I'm wondering if they have this sort of pathology. Can you help me? And the radiologist says, okay, yes, I see that. There's definitely this pathology going on. I see this other one. Here's what I think this could be, right? So the radiology report is not a ground truth label. It's a conversation. And it's very important to factor in this indication when you are understanding an image with its impression. So a lot of methods will sort of just label the image with the impression. But if I didn't ask you about, say, fractures in the image, then you're not going to mention it in the radiology report, even if there is one, or at least you're not necessarily going to. So if we look at the sort of workflow of a pneumonia admission, there's a lot of information which drives this clinical context, right? So if a patient comes in from the community, there'll be triage, there'll be a note, they'll have their vital signs taken, there'll be a history, there'll be some diagnosis that is done, some diagnostics, excuse me. So blood work, the chest x-ray comes in here, but also with a physical. And all this sort of information is combined together in order to understand what's going on with the patient. And we'll hear more about sort of combining multimodal clinical information with the chest x-ray later. And doing something like this is very important, for example, with a diagnosis like pneumonia, because pneumonia is actually a clinical diagnosis. You cannot make a diagnosis of pneumonia from a chest x-ray alone. You need certainly the information from the chest x-ray is useful, but you also need systemic sort of signs that the patient has some sort of illness. It cannot be done from the chest x-ray alone. So in some instances, you absolutely have to use all this information. Otherwise, you just don't have the full picture. So with that, I hope you learned a little bit about the data generating process. I've included a Colab notebook where you can run through with some saliency maps and see some sort of flaws there and get a sense of how these models work and maybe try them out yourself. And of course, check out the other sessions which go into more detail about multimodal clinical data modeling or improving NLP models. And I'd also like to just thank all the institutes and the people who made all this data available. We couldn't do any of this research if these people didn't take the leap and just put all this information out into the sort of public domain for public benefit. So thank you to them, especially. We wouldn't be here without them. And thank you for your attention.